a couple of concepts in this chapter that I think I'm going to show you in the lab during our lab time tonight. They're better demonstrated in person with models, so with a molecular model kit. But the first part we don't need a model kit for, to discuss carbohydrates. And this is another one of those subjects where if you've studied biology before, I'm sure you've heard about glucose in some way or another, or maybe maltose, which is a disaccharide, or what are some other sugars you might have heard of? Lactose. Everybody's heard of lactose intolerance, I'm sure. Anyhow, where do carbohydrates come from? Carbohydrates are synthesized by photosynthesis in plants, and some common examples of carbohydrates would be things like grains, cereals, bread, sugarcane. And glucose is a major energy source in the body. And glucose has the molecular formula C6H12O6. But in fact, many, or several, I should say, carbohydrates have that same molecular formula. Some interesting facts about glucose, our major energy source. It says here that 1 gram of digested carbohydrate gives you about 4 kilocalories of energy, which is roughly equivalent to the same amount of energy, or roughly equivalent to the amount of energy found in 1 gram of protein. 1 gram of fat, however, has a little bit more than double the amount of energy per gram. Complex carbohydrates, like starches that are found in things like potatoes or sweet potatoes or yams, those are the ones that are considered best for our diet. Excuse me. And the USDA recommends that about 45 to 65% of our calories come from carbohydrates each day. So probably a higher protein diet than most people eat on a regular basis. Basic carbohydrate types. We are concerned with all of these types that are on this slide. First are monosaccharides, and you've also heard of fructose, I'm sure, which is fruit sugar, glucose. And what monosaccharide means is, I'm sure you've all figured this out, is that mono means one. So one sugar. When we take 2 sugar molecules and we link them together, we make what is called a disaccharide. And disaccharides are very common. In fact, table sugar, which is sucrose, which is the sugar you use for baking or put in your coffee, that is a disaccharide made from fructose and glucose. And then lactose is made from glucose and galactose. It is the milk sugar. And what's important is that you know that when we have a disaccharide or any kind of polysaccharide, what they're called, is that the linkage, or the way that the sugar link molecules are linked together, is called a glycosidic bond. So a glycosidic bond, and we'll talk quite a bit about glycosidic bonds, because glycosidic bonds are also a form of an acetal. And you remember acetals and hemiacetals that we spoke about earlier on in the course. In fact, there was a question about those on the last exam. If you link between 3 and 10 monosaccharides together, you get what's called an oligosaccharide. And polysaccharides are when you have something bigger than that. So things like starch are polysaccharides, glycogen, cellulose. So glycogen is the major form of storage of glucose in the body. Cellulose makes up the rigid walls of plant fibers. And of course, starch is a complex carbohydrate found in some foods. A little bit more about monosaccharides. Monosaccharides are composed of carbon, hydrogen, and oxygen, and they have the basic formula shown here, CH2ON, where N is any integer from 3 to 7. In fact, that's where the word carbo, so I'll put it here, carbo comes from the carbon, carbo, right? And hydrate comes from the fact that for every water molecule, you have a carbon. So carbohydrate. Mind blown, right? Anyhow, many monosaccharides also contain chemical modifications. So what it means is that not every single carbohydrate out there has just carbon, hydrogen, and nitrogen. Some of them have amino groups like lactosamine or things like that, or phosphate groups. We're not really going to concern ourselves a ton with these, but just so you know, not every carbohydrate is purely made from carbon, hydrogen, and oxygen. You should be aware of that. Naming monosaccharides, the good news is you don't have to know the actual name of every monosaccharide out there. That would be very difficult to do. But it says here that monosaccharides are named on the basis of two things: the number of carbon atoms, which is the second bullet point, the number of carbon atoms, and functional groups. So if in our carbohydrate, if we have a ketone, we call it a ketose. And if we have an aldehyde, we call it an aldose. So let me show you what that means. If you take a look at these two carbohydrates right here, you look at the carbon that's at the top. So going this way, going up like this, we always write our carbohydrates in specific orientation. So if you look at the carbon that's at the top, okay, carbon number 1, if that is an aldehyde, we call it an aldose. And if it is a ketone, which is highlighted in pink here, then we call it a ketose. Pretty simple, right? So if it's an aldehyde at the top, it's an aldose. And if it's a ketone at the top, it's a ketose. Nothing more than that. The next thing is that we count up the number of carbons in the entire molecule. So main skeleton is just another way of saying the molecule. If it has 3, it's a triose. If it has 4, it's a tetrose. 5 is a pentose. And 6, we call it a hexose. And then combining both of those together gives us even more information. Let me show you what I mean by that. If we take a look at this molecule right here, let's focus on this little tiny molecule. First of all, you can see that it's an aldose because we have an aldehyde here. So we know that it is, in fact, an aldose. The reason we call it a triose is because it has 1, 2, 3 carbon atoms. So we know that it is, in fact, a triose. When you put all of those together, aldose and triose, we call it an aldotriose. The same thing would apply to the next two molecules. So this first one actually has a common name, which is which is D-glyceraldehyde, and we'll look at that molecule a few times. And then we have D-glucose and D-fructose. If I go back to my D-glucose molecule, wherever the heck it was, are you kidding me? If I go back to my D-glucose molecule, you can see that D-glucose is in fact an aldose because it has an aldehyde at the top, an aldehyde functional group, and it is a hexose because it has 1, 2, 3, 4, 5, 6 carbons. So we call it an aldohexose. D-fructose, which is shown right here, is a ketose because it has a ketone here. I'll be careful with my pencil. And it also has 6 carbons, so we call it a ketohexose. So there you go. So that's, kind of our introduction to nomenclature. So the good news is you don't really have to know a whole lot more than that for carbohydrate nomenclature. You don't have to memorize the structure of glucose or glyceraldehyde or fructose, any of those things. You should just know how to identify a ketose, an aldose, a triose, tetrose, pentose, and hexose. Let's move on and talk about stereochemistry. And you noticed that on the previous slide, I said D-glyceraldehyde, D-glucose, and what else? D-fructose. Well, I can prefix sugars with either the letter D or L, and those prefixes describe one of 2 isomeric forms. It says here that these isomers differ in what? The spatial arrangement of atoms and are what is known as stereoisomers. So stereoisomers, their connectivity is the same. The way the atoms are connected together is identical. The difference in stereoisomers is the spatial arrangement of the atoms, or the way that atoms are arranged in space. So stereochemistry is the study of different spatial arrangement of atoms. And this is something that I'm going to talk to you about tonight in the lab a little tiny bit, because it's very difficult to get this point across without me showing you some demonstration with molecular models. It'll only take 5 minutes though, so don't worry about that a whole lot. It says here that not only can I have D-glyceraldehyde, let's go back. Okay, here's our D-glyceraldehyde molecule right here. Not only can I have the D-glyceraldehyde, I can also have L-glyceraldehyde. Okay, and they are non-superimposable mirror image molecules, and they are called enantiomers. Enantiomers is the definition of enantiomers is molecules that are non-superimposable mirror images. And if you're thinking, well, come on, if I reflect something in the mirror, isn't it superimposable? No, absolutely not. Okay, and let me prove it to you. If you take a look at these two molecules shown here at the top, these are mirror images of each other, right? There's a reflection right down the middle. But if you try to take this molecule and put it on top of this one, you'll never be able to align all of the atoms. Think about it. If you take this model right here and plop it on top of the other one, the red and the red are in the same spot. The green and the green are in the same spot. But look, my purple would overlap with the yellow, and this yellow would overlap with a purple. So they are, in fact, not the same compound. Okay? They're non-superimposable mirror images. The same, you have another example of non-superimposable mirror images at the end of your wrists. They're called your hands. If you put your two hands up, minus your rings or whatever, but they're mirror images of each other. In fact, let me show you. Let me go back to Teams. Okay. So if you look at my two hands, they're mirror images of each other, right? Except for my wedding ring, they're mirror images, but they're non-superimposable. I can't put one on top of the other. I don't get the same thing. So that is what enantiomers are, okay? They're non-superimposable mirror images. Sorry, I just kicked myself out of the meeting. Anyhow, let me go back here. Go back to my slides. Excuse me. Okay, so non-superimposable mirror images are enantiomers. So chirality is when you have a carbon atom that has 4 different groups bonded to it, it is called a chiral carbon atom. Any molecule containing a chiral carbon atom can exist as a pair of enantiomers, which are non-superimposable mirror images. The chirality in glyceraldehyde, that little molecule I circled in red a few minutes ago, which is the simplest possible carbohydrate, is conveyed by a chiral carbon, right? How do we know that it has a chiral carbon? Because it has a carbon in it that has four different groups bonded to it. Let me just write a little note here. What it says is 4 different groups, okay? Not atoms, but groups. Okay, not atoms, but groups. Larger biological molecules often have more than one chiral carbon. Say, for example, cholesterol. Cholesterol has 8 chiral carbons in it. So, you can have a lot of chiral carbons in a molecule. Let's get back to that little, unassuming molecule, the glyceraldehyde molecule. Now you can see here that I have D-glyceraldehyde and L-glyceraldehyde, the two enantiomers. Okay, it says here the difference between these two is that the D isomer has the hydroxyl, the OH, on the right, shown right here, and the L has it on the left. Now notice if I have a mirror here, you can see that these are mirror images of each other. But if I try to take this molecule and plop it on top of here, you can see that this hydroxyl would be over here. So they are not, in fact, going to overlap with each other, okay? They are non-superimposable mirror images. That's the definition of enantiomers. What else do we know? They have 4 different groups bound to the chiral carbon. So let me highlight what is the chiral carbon. This carbon is chiral. Okay, it says here, we call this a chiral center. Now remember, I said 4 different groups. I didn't say 4 different atoms. I said 4 different groups. What are the 4 groups that this carbon circled in blue is attached to? It's attached to a hydrogen atom. It's attached to a hydroxyl. A hydrogen and a hydroxyl are 2 different groups. It's attached to this CH2OH. That's a different group. And it's attached to this aldehyde. So all 4 of those things that are in my red circles, those are all different. So therefore, that's 4 different groups. The reason I'm stressing this is because sometimes students will get caught in the trap and they'll say, hey, it's attached to a carbon and a carbon. Those are identical. It's not a chiral center. No, 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 no. You have to look at the entire group and take the entire group into account. Oops. All right, let's keep moving here. So this just shows the mirror images of D and L glyceraldehyde shown right here like that. Okay. And then we move on to something called optical activity. Optical activity. Just give me 1 second. Okay, so optical activity. Enantiomers are also called optical isomers. And enantiomers interact with plane polarized light to rotate the plane of the light in opposite directions. This interaction with plane polarized light is called optical activity. And optical activity is a tool that we can use to distinguish between enantiomers, so these kinds of isomers. And it's measured in a device called a polarimeter. All right. Let me see here. Who's ready to call it quits? And we'll continue on with this later on. Who says, I am? Okay. Okay, me too, Jasmine. I'm tired and I'm starving. So, and I'm sure you are too. Although you guys can eat while I'm talking. I can't eat. I'm really hungry. So why don't we call it quits for now? And I'll meet you in the lab at 8 p.m. Cool? And I will bring all of your graded exams and your graded lab reports. I have them all done. So I think your exams are on my dining room table, but I'm going to remember to bring them. All right. So I'll see you all at 8 p.m.